Tonight, we follow the long journey of a comet. Welcome to the Orbit for Sleep channel. Let us follow the orbit of science and drift gently toward sleep. A faint point of light begins to move against a background that has not changed for thousands of years. At first, it is indistinguishable from an ordinary star. Night after night, its position shifts slightly, slow enough to escape casual notice, steady enough to confirm that it does not belong to the fixed patterns of the sky. What appears to be a quiet visitor has already been traveling since long before Earth developed oceans. This object is a comet that formed in the cold outer regions of the early solar system, far beyond the orbit of the outer planets. More than 4.5 billion years ago, leftover ice and dust from planet formation were scattered into distant reservoirs by the gravity of the growing giant planets. One of these reservoirs is the Oort cloud, a vast spherical region surrounding the solar system at distances tens of thousands of times farther than Earth is from the Sun. A slow gravitational disturbance from a passing star or the tidal pull of the Milky Way can redirect one of these frozen bodies inward. Once redirected, the comet begins a long fall toward the Sun. Its speed increases steadily as gravity converts distance into motion. Near the outer planets, the surface remains unchanged, locked in deep cold. As the comet approaches the inner solar system, sunlight becomes intense enough to heat its surface. Ice does not melt in the usual way. It changes directly from solid to gas in a process called sublimation. Released gas drags fine dust from the surface, forming a cloud around the comet known as a coma. Pressure from sunlight and the steady stream of particles flowing outward from the sun push this material into long tails. One tail is made of dust and follows the curve of the comet's orbit. The other is made of electrically charged gas and always points directly away from the Sun. These structures grow larger as the comet approaches the interplanetary region and fade again as it retreats. A useful comparison comes from everyday experience with steam on a cold morning. When warm water meets cold air, invisible molecules suddenly become visible as a drifting cloud. The comet's tail is produced by the same physical principle, scaled to millions of kilometers. The discovery of long-period comets reaching back to distant reservoirs became clear in the mid-1900s, when astronomer Jan Ott analyzed their orbits and showed that they originated far beyond the known planets. These visitors carry material that has remained mostly unchanged since the earliest stage of solar system formation. The long journey of a comet is therefore not only a path through space, it is a movement through time, carrying ancient matter from the outer darkness into the warm inner regions, briefly revealing the earliest conditions of the solar system before returning again to deep space. The journey of a comet begins in regions of the solar system where sunlight has almost no influence. Far beyond the outer planets lies a vast collection of frozen debris left over from the formation of the sun and planets. In these distant zones, temperatures remain close to absolute zero, and motion is slow and stable for millions of years. During the early stage of the solar system, small, icy bodies formed from water ice, carbon dioxide, methane, ammonia, and fine dust. These materials never became part of a planet. Instead, the growing gravity of the giant planets scattered many of them outward, Some settled into the Kuiper belt beyond Neptune. Others were pushed much farther away into the distant Oort cloud. In these regions, a comet can remain unchanged for billions of years. A comet's journey begins when this long balance is disturbed. A passing star, the slow tidal pull of the Milky Way, or the combined gravity of nearby objects slightly alters the comet's path. The change is often so small that it would be undetectable on human timescales. Yet over thousands or millions of years, the altered trajectory becomes a slow fall toward the inner solar system. As the comet moves inward, its speed increases under the steady pull of the sun's gravity. At great distances, the surface remains frozen and inactive. Only when the comet reaches the region near the orbit of Jupiter does heating begin to affect its outer layers. Ices transform directly into gas, releasing trapped dust. This marks the physical beginning of its visible journey. A simple everyday comparison is a block of ice taken from a freezer into a warm room. At first, it appears unchanged. With time, invisible warming causes moisture to form and spread. The comet experiences a similar transition, but across distances measured in hundreds of millions of kilometers. The first scientific understanding of this process developed gradually through orbital studies in the 1700 and 1800. Precise tracking revealed that many comets followed extremely stretched paths that could not be produced inside the planetary region alone. This evidence showed that their origin must lie far beyond the known planets. A comet's journey, therefore, begins not with motion we can easily observe, but with a quiet gravitational shift in the farthest cold reservoirs of the solar system, where time moves slowly and matter remains preserved from the earliest era of planetary formation. Long-period comets follow paths that stretch far beyond the familiar scale of planetary orbits. Unlike planets, which repeat their paths every few years, these comets move along elongated ellipses that can take hundreds of thousands to millions of years to complete a single revolution around the Sunday. The reason for these immense return times lies in basic orbital physics. The farther an object travels from the Sun, the more slowly it moves. At the outer edge of the Oort cloud, a comet drifts at extremely low speeds because the Sun's gravitational pull is weak at such distances. Once redirected inward, gravity steadily accelerates the comet as it falls toward the inner solar system. After it swings past the Sun, the same physics carries it back outward again, where its motion gradually slows for most of its journey. This type of orbit is governed by the conservation of energy and momentum. The comet exchanges gravitational potential energy for kinetic energy as it falls inward and reverses this exchange as it climbs back outward. Because the distance involved spans tens of thousands of times the Earth-Sun distance, the round trip naturally requires vast stretches of time. An everyday comparison can be found in throwing a ball straight upward. Near the ground, it moves quickly. Near the top of its path, it slows almost to a stop before falling again. A long-period comet behaves in the same way, except that the upward and downward motion unfolds across the full diameter of the solar system and beyond. The extremely long return periods were confirmed through precise orbital measurements, beginning in the late 1600s and continuing into the modern era. Astronomers found that some comets recorded in ancient historical documents would not reappear within any human lifetime. Their calculated paths showed periods far exceeding recorded history. Because of these immense orbital scales, many long-period comets observed today are likely making their first visible approach to the Sun since the solar system formed. Others that pass through the inner region may not return for millions of years. Their slow, stretched paths reveal how the structure of the solar system extends far beyond the planetary region into deep interstellar space. The first close approach of a comet toward the Sun marks a turning point in its long existence. For most of its life, the comet remains frozen and inactive in the outer reservoirs of the solar system. During this early stage, it reflects almost no sunlight and releases no visible material. Its motion is governed only by weak gravitational pulls and slow drift. As the comet falls inward for the first time, solar radiation steadily increases. At large distances, the surface temperature remains far below the point at which any visible change occurs. Once the comet reaches the region near the orbit of the giant planet, solar heating begins to penetrate the outer layers. Volatile ices that have remained stable for billions of years start to sublimate, change directly from solid to gas. This physical transformation initiates the comet's active phase. Gas escaping from the surface carries fine dust into surrounding space, forming an expanding envelope known as the coma. With continued approach, the increasing solar wind and radiation pressure shape this material into extended tails that grow in length as the Sun is approached. The motion accelerates rapidly at this stage because gravitational force increases sharply with decreasing distance. A familiar comparison can be found in a spacecraft entering Earth's atmosphere. At high altitudes, the crust remains cold and unaffected. As it descends into denser layers, heating increases quickly and dramatic physical changes occur. The comet experiences a similar transition, driven not by air, but by sunlight and solar particles. The first scientific understanding of this transformation developed as repeated comet observations became possible in the 16th and 17th centuries. Early astronomers noted that comets brightened rapidly near the Sun and faded again as they moved away. Later spectroscopic studies in the 19th century revealed that the glowing coma consisted of gas released by solar heating. The first fall toward the Sun therefore represents the moment when a comet changes from a silent, frozen body into an active, visible object. This transition exposes material that has been locked away since the earliest stage of planet formation, and briefly connects the cold outer regions of the solar system with the warm inner planetary zone. Once a comet has passed near the Sun, its path is permanently reshaped by gravity. The intense acceleration it experiences during its closest approach does not end its journey. Instead, it redirects the comet back toward the outer solar system along a new but continuously flowing orbit. The motion does not reverse sharply. It bends gradually, guided by the same gravitational rules that shaped its inward fall. This curved path is described by an elongated elliptical orbit. Near the Sun, the comet moves at its greatest speed. Far from the Sun, it drifts slowly for the majority of its journey. Yet the motion never truly stops. Even at the outermost reaches of its trajectory, the comet continues forward under the lingering influence of solar gravity. Each return toward the inner solar system subtly alters the comet's future path. Gravitational interactions with planets, especially Jupiter, can shift its orbit inward, outward, or even eject it completely from the solar system. Some comets are gradually captured into shorter, repeating orbits. Others are thrown into interstellar space, ending their connection to the Sun forever. An everyday comparison can be seen in a stone skimming across the surface of water. Each contact bends the stone's direction slightly. Some stones slow and sink, others skip forward and disappear beyond view. The comet's orbit is shaped in a similar way through repeated gravitational encounters. The understanding that comet paths are continuously shaped by planetary gravity emerged clearly in the 1700s through the work of astronomers such as Edmund Halley. By calculating the repeated return of a single comet, Halley demonstrated that these objects follow predictable but flexible paths shaped by gravitational interaction rather than random motion. The path that bends but never stops reflects the fundamental nature of celestial motion. A comet does not travel along a straight line or a closed circle. It follows a changing curve shaped by distance, gravity, and time, moving endlessly between the cold outer regions and the warm inner zones of the solar system, until its material is exhausted or its path is finally broken. At the center of every comet lies a compact, solid body known as the nucleus. This nucleus is the true physical core of the comet and contains nearly all of its mass. Most comet nuclei measure only a few kilometers across, yet they carry material that has remained preserved since the earliest stage of solar system formation. The nucleus is made primarily of water ice mixed with frozen carbon dioxide, carbon monoxide, methane, ammonia, and fine mineral dust. These components are bound together into a weak, porous structure. Rather than being a solid block of ice, the nucleus resembles a loosely packed mixture of frozen grains with empty spaces between them. This structure allows heat and gas to move easily through the interior when the comet becomes active. Direct measurements of comet nuclei became possible in the late 1900s and early 2000 through spacecraft missions. The Giotto mission to Halley's Comet in 1986 provided the first close images of a nucleus. Later missions, such as Deep Impact and Rosetta, revealed irregular shapes, dark surfaces, and unexpectedly low densities. These observations confirmed that comet nuclei are not solid ice spheres, but fragile assemblies of frozen material. The dark surface of a nucleus results from repeated exposure to sunlight. As ices slowly escape over many passages near the sun, non-volatile dust accumulates on the surface and forms an insulating crust. Beneath this thin outer layer, large amounts of pristine ice can remain intact for billions of years. A familiar everyday comparison is a scoop of packed snow mixed with dirt during winter. From the outside, it looks dark and solid. Inside, it still contains bright ice crystals and trapped air. The comet nucleus exhibits a similar layered structure on a planetary scale. The frozen core of a comet therefore acts as a natural storage container for the original ingredients of the solar system. When sunlight unlocks this material during each passage near the sun, the nucleus releases gas and dust that briefly reveal the physical conditions that existed before planets fully formed. The material that forms a comet is a frozen mixture of simple molecules and fine dust, that date back to the earliest phase of solar system formation. Water ice is the dominant component by volume. Along with it are frozen carbon dioxide, carbon monoxide, methane, ammonia, and traces of more complex organic compounds. These substances are embedded within microscopic mineral grains made of silicates and metals. In the cold outer regions of the solar system, these materials remain locked in solid form. Temperatures are so low that even gases that would normally evaporate on Earth remain frozen for billions of years. This deep cold prevents chemical change and preserves the original composition of the comet with little alteration. As a comet approaches the Sun, different materials become active at different distances. Carbon monoxide begins to escape first, far beyond the orbit of Jupiter. Carbon dioxide follows closer in. Water ice requires significantly stronger heating and becomes dominant only when the comet reaches the inner solar system. This layered release of gas reveals that the comet is not chemically uniform, but made of multiple volatile components with different evaporation thresholds. Dust is released alongside these gases. Fine particles are lifted from the surface and carried outward by the escaping flow. These grains range from microscopic powder to small pebble-sized fragments. Once released, they drift behind the comet and contribute to its visible tail. A simple, everyday comparison can be found in a mixed, frozen drink removed from a freezer. The most volatile ingredients begin to escape first, while heavier components remain frozen longer. The comet behaves in a similar physical sequence under solar heating. Spectroscopic studies in the 1900s allowed astronomers to identify these materials by analyzing the light emitted by the comet's coma. Each molecule produces a distinct pattern of light, allowing scientists to map the chemical inventory of the nucleus without direct contact. Dust, ice, and ancient gas together form a physical record of the environment that existed before the planets fully assembled. By observing how these materials respond to sunlight, scientists gain direct access to the original building blocks of the solar system. The visible tail of a comet forms as a direct result of solar heating and the flow of energy from the sun into the surrounding space. When a comet approaches the inner solar system, heat penetrates the surface of the nucleus and causes frozen gases to sublimate. This means they change directly from solid to gas. This process releases a continuous stream of material outward from the nucleus. As gas escapes, it carries fine dust particles with it. The expanding cloud of gas and dust surrounding the nucleus becomes the coma. This region can grow to tens of thousands of kilometers in diameter. Within the coma, sunlight and charged particles from the sun interact with the released material and begin shaping it into extended structures. Radiation pressure from sunlight pushes dust particles, creating the dust tail. At the same time, the solar wind is a steady stream of charged particles flowing outward from the sunday. This solar wind sweeps ionized gas directly away, forming the iron tail. These two forces act continuously as the comet moves forward along its orbit. The result is the gradual formation of long, luminous tails that grow more pronounced as the comet approaches the sunday. The direction of the tail is not controlled by the comet's motion through space, but by the outward flow of energy from the sunday. This is why comet tails always point away from the sun, regardless of whether the comet is moving toward it or away from it at that moment. A familiar everyday comparison is smoke drifting from a moving train on a windy day. The train continues along its track, but the smoke is carried in the direction of the wind rather than directly behind the engine. In the same way, the comet travels along its orbit, while its released material is shaped by solar forces. Systematic photographic observations in the 19th century allowed astronomers to trace how comet tails change in length and orientation as the comet moves along its path. These observations provided the first clear evidence that sunlight and solar particles actively control the structure of the tail. A comet creates its tail not through internal activity like a star, but through continuous interaction with external energy from the sun. The tail is therefore a visible record of the invisible forces that dominate the space between the planets. A comet often displays two distinct tails at the same time, each formed by a different physical process. Although they may appear similar at a distance, these tails behave in fundamentally different ways and respond to different forces coming from the sun. One of these is the dust tail. It is made of small, solid particles released from the nucleus as gas escapes during heating. These dust grains are pushed outward by radiation pressure from sunlight. Because the particles retain much of their original orbital motion, the dust tail follows a curved shape that roughly traces the path the comet has traveled. The curvature reflects the gradual separation between the drifting particles and the moving nucleus. The second tail is the ion tail, made of gas that has been electrically charged, ionized by ultraviolet radiation from the sun. Once ionized, the gas becomes highly sensitive to the solar wind. The solar wind flows directly outward from the sun at high speed, carrying the charged particles with it. This produces a straight, narrow tail that always points directly away from the sun. These two tails can shift rapidly in size and shape as solar conditions change. Variations in solar wind strength can cause sudden kinks or breaks in the ion tail. The dust tail responds more slowly, changing shape gradually as particles spread out along the comet's orbit. A simple everyday comparison is the difference between heavy dust and invisible vapor released into moving air. Dust drifts slowly and follows curved paths. Vapor is swept quickly along straight lines by the airflow. The two comet tails behave in the same physically distinct ways under solar forces. The dual nature of comet tails was established through careful telescopic observation in the late 19th century, when astronomers recognized that a single explanation could not account for both their curved and straight components. Modern spacecraft measurements later confirmed the electrical nature of the ion tail. The presence of two distinct tails reveals that a comet is shaped simultaneously by sunlight and by the invisible stream of particles flowing outward from the sun. Together, these forces transform simple released material into one of the most recognizable structures in the night sky. Each time a comet passes near the sun, it undergoes physical change that permanently alters its structure. The intense heating caused by solar radiation removes part of the comet's surface with every close approach. Gas escapes from the nucleus, carrying dust with it into space, and this continuous mass loss gradually reduces the comet's overall mass. The most volatile ices disappear first. Carbon monoxide and carbon dioxide are lost at large distances, while water ice dominates closer to the sun. Over repeated passages, the outer layers become depleted of easily evaporated material. As a result, later returns often produce weaker activity than earlier ones. With time, a thick crust of dust can form on the surface. This layer acts as an insulating blanket, limiting how deeply heat can penetrate into the interior. Beneath that crust, pockets of ice may remain trapped and inactive until fractures open or the crust collapses. This explains why some comets show sudden outbursts of activity when new volatile material becomes exposed. Thermal stress also cracks the nucleus. The rapid cycle of heating near the sun and cooling in deep space causes expansion and contraction of materials. These repeated stresses weaken the internal structure and can lead to fragmentation. Several well-observed comets in the modern era have split into multiple pieces during close solar passages. An everyday comparison can be found in a rock, repeatedly heated in a fire and then cooled in air. Over time, the surface flakes, internal cracks form, and the object becomes structurally weaker. The comet experiences the same physical fatigue on a cosmic timescale. Systematic monitoring of comet brightness from the 18th century onward revealed that many periodic comets grow dimmer over repeated returns. Spacecraft observations in the late 20th century confirmed direct mass loss and surface erosion during solar encounters. Each close passage near the Sun therefore acts as a slow process of aging for a comet. Through repeated heating, erosion, and mechanical stress, the nucleus is steadily transformed until its volatile material is exhausted or the object breaks apart entirely. One of the most important questions about comets concerns their possible role in delivering water to the early Earth. Billions of years ago, during the final stages of planet formation, Earth was a hot, violent world shaped by frequent impacts. Much of its original water may have been lost during this early period due to intense heating and atmospheric escape. Comets formed in the cold outer regions of the solar system contain large amounts of frozen water. When some of these objects were scattered inward during the early dynamical reshaping of the planetary system, they frequently crossed Earth's orbit. Repeated impacts over millions of years would have released water and volatile gases directly onto the surface. Evidence for this idea comes from the study of isotopes, slightly different forms of the same element. Water contains hydrogen, and the ratio of its heavy form, called deuterium, to normal hydrogen acts as a chemical fingerprint. Measurements of this ratio in certain comets closely resemble the ratio found in Earth's oceans. This similarity suggests that at least part of Earth's water could have originated from cometary material. Further support comes from spacecraft missions that directly sampled comet composition. The Rosetta mission to Comet 67P in the 2010 seconds measured the isotopic makeup of water vapor released from the nucleus. These missions demonstrated that comets carry not only water, but also organic molecules that are important for prebiotic chemistry. A simple everyday comparison is the gradual filling of a reservoir through repeated small rain events. No single storm creates the lake, but over time, the accumulated input becomes substantial. In the same way, countless small comet impacts could have contributed significant amounts of water to the young Earth. The idea that comets helped supply Earth's water emerged in the mid-20th century as models of planetary formation became more precise. Today, most scientists conclude that both comets and water-rich asteroids likely played roles, with the exact balance still under active study. If even a fraction of Earth's oceans came from comets, then these distant frozen travelers influenced not only the planet's surface, but also the long-term conditions that allowed life to develop. Comets preserve material that has remained largely unchanged since the earliest stage of solar system formation. Because they formed far from the sun and spent most of their existence in deep cold, their internal chemistry avoided the intense heating and alteration that reshaped planets and many asteroids. For this reason, comets function as natural time capsules of the early solar system. Inside a comet's nucleus are simple ices, dust grains, and primitive organic compounds that condense directly from the original cloud of gas and dust surrounding the young sundae. Unlike materials on Earth, which have been recycled by plate tectonics, erosion, and biological activity, these components have remained isolated for billions of years. This preservation allows scientists to study conditions that no longer exist anywhere else in the solar system. By analyzing the gases released as a comet becomes active, researchers can reconstruct the temperature, pressure, and chemical environment that existed when the planets were still forming. Spacecraft missions in the late 20th and early 21st centuries provided the first direct access to this ancient material. The Stardust mission in 2006 returned dust samples from Comet Wild 2 to Earth. Laboratory analysis revealed high-temperature minerals mixed with cold outer solar system ices, showing that material from very different regions of the early solar system became blended within comets. Spectroscopic observations from ground-based telescopes also allowed scientists to identify complex organic molecules in cometary comas. Some of these molecules are the same types used in basic biological chemistry, including simple amino acid precursors. A useful, everyday comparison is a sealed archive stored deep underground. While the surface world changes, the contents inside the archive remain protected from weather, light, and biological activity. The comet nucleus plays a similar protective role on cosmic scale. Because of this preservation, each close passage of a comet near the Sun briefly opens a window into the solar system's earliest physical and chemical state. These brief appearances provide information that cannot be obtained from any planet or moon, making comets one of the most valuable natural records of cosmic history. For most of human history, comets were not understood as physical objects governed by natural laws. They appeared without warning, changed shape in the sky, and vanished again. Because of this unpredictable behavior, ancient civilizations often interpreted comets as signs connected to fate, disaster, or major political change. Early records from China, dating back more than 2,000 years, contain some of the most systematic descriptions of comets. Court astronomers carefully documented the position, brightness, color, and duration of these objects because they were believed to signal events affecting the emperor and the state. These records later became valuable data for modern orbital calculations. In the ancient Mediterranean world, comets were commonly viewed as omens. Greek and Roman writers described them as flaming swords or celestial torches. The appearance of Halley's comet in 1066 was later linked by medieval chroniclers to the Norman conquest of England, reinforcing the belief that comets announced dramatic change. Other cultures developed different symbolic interpretations. In parts of the Americas, comets were associated with cycles of renewal or destruction within a broader cosmological framework. In many traditions, the same physical event was woven into local systems of meaning shaped by religion, politics, and social structure. Consider the analogy of the sudden appearance of an unexpected natural event, such as a total solar eclipse in a community without scientific prediction. The event itself is physical, but the meaning assigned to it arises from human interpretation rather than natural law. Scientific understanding of comets began to replace symbolic explanation during the 16th and 17th centuries, as careful telescopic measurements showed that comets moved through space beyond Earth's atmosphere. The work of astronomers such as Tycho Brahe helped establish that comets were celestial bodies rather than atmospheric phenomena. Although modern science now explains comets through gravity and solar physics, their historical role as symbols of uncertainty and change reflects how deeply human perception has been shaped by rare and unpredictable events in the sky. The transition from symbolic interpretation to scientific observation of comets began with precise measurement. For centuries, comets were thought to exist within Earth's atmosphere, changing shape as they drifted through air. This view persisted because their diffuse appearance resembled clouds or fire rather than solid bodies. The first decisive shift occurred in 1577, when a bright comet became visible across Europe. Astronomer Tycho Brahe measured its position against the distant background stars from different locations. By comparing these observations, he showed that the comet exhibited no measurable parallax relative to the stars. This meant it had to be far beyond the moon, and therefore a true celestial object. This realization placed comets within the same physical universe as planets. It implied that comets followed paths through space governed by gravity rather than random motion through the atmosphere. Later, in the late 17th century, Isaac Newton's laws of motion and gravity provided the mathematical framework needed to calculate those paths. Edmund Halley applied these laws to historical comet records and recognized that several bright comets observed in 1531, 1607, and 1682 were the same object following a repeating orbit. He predicted its return in 1758. When the comet reappeared on schedule, it confirmed that comet motion could be understood and predicted using the same physical principles that govern planetary motion. A simple, everyday comparison is tracking a distant airplane by repeated measurements from different locations. Without precise timing and geometry, its true distance remains uncertain. With careful measurement, its path and position become clear. The same method allowed astronomers to move comets from the realm of mystery into the domain of measurement. By the early 18th century, comets had become recognized as members of the solar system rather than atmospheric signs. This change marked one of the key moments when observational science replaced symbolic explanation in humanity's understanding of the sky. The first scientific observation of comets therefore transformed them from unpredictable omens into predictable travelers, revealing that even the most irregular objects in the sky obey the same fundamental laws of motion. Throughout recorded history, the appearance of several major comets has coincided with periods of social and scientific change. While comets did not cause these events in a direct physical sense, their sudden visibility often influenced human perception, behavior, and historical interpretation. One of the most well-documented cases is the appearance of Halley's Comet in 1066. The comet was visible for months across Europe and was recorded in the Bayeux Tapestry as a sign preceding the Norman invasion of England. For observers at the time, the comet reinforced the belief that dramatic changes in power were linked to celestial signs. Another historically significant appearance occurred in 1456, when Halley's Comet passed close to Earth during a period of conflict between European states and the Ottoman Empire. The comet was widely associated with fear and uncertainty. Its return later provided astronomers with long-term data that helped confirm the periodic nature of cometary orbits. In the modern scientific era, the impact of Comet Shoemaker-Levy 9 on Jupiter in 1994 marked a turning point. For the first time, humans directly observed a comet collide with a planet in real time. The visible scars left in Jupiter's atmosphere permanently demonstrated that large impacts remain an active process in the solar system. A useful everyday comparison is the way rare natural disasters shape public awareness long after they occur. The event itself may be brief, but its influence on planning, belief, and scientific attention can last for decades. These historical encounters did not change the physical laws governing the solar system, but they changed how humans understood their place within it. Each widely observed comet reinforced the idea that Earth exists within an active and sometimes violent planetary environment, rather than a static and protected one. When a comet crosses the human historical record, its brief appearance becomes part of long cultural memory, linking short-lived human events to the much longer timescales of celestial motion. Comets and asteroids are often grouped together as small bodies of the solar system, yet they differ fundamentally in composition, origin, and behavior. Asteroids formed primarily from rocky and metallic material in the warmer inner regions of the early solar system. Comets formed in the cold outer zones, where ices could remain solid and volatile compounds could accumulate. Because of this difference in origin, asteroids are dense and relatively stable when exposed to sunlight. Comets, in contrast, contain large amounts of frozen gas. When both types of objects approach the sun, asteroids change little, while comets become highly active as their ices sublimate and release gas and dust. Their surfaces reflect this contrast. Asteroids usually maintain solid, cratered exteriors shaped by collisions. Comet nuclei develop evolving surfaces that change with each solar passage as material is lost and dust crusts form. Over time, repeated heating can strip a comet of its volatile content until it begins to resemble a dark, inactive, asteroid-like object. Orbital behavior also differs on average. Many asteroids travel in relatively stable belts between Mars and Jupiter. Comets often follow highly elongated orbits that carry them from distant outer reservoirs deep into the inner solar system. These stretched paths expose them to a far wider range of temperatures and radiation environments. A simple everyday comparison is the difference between a stone and a block of ice exposed to sunlight. The stone warms but remains solid. The ice rapidly changes state, releases water, and reshapes its surface. The physical response of comets and asteroids to solar energy follows the same basic distinction. Modern classification became precise in the 19th and 20th centuries as spectroscopy and orbital analysis matured. These tools revealed that apparent similarities in brightness hid deep differences in physical structure and chemical composition. Comets and asteroids therefore represent two contrasting outcomes of the same planetary formation process. One preserves the rocky skeleton of the early solar system. The other preserves its frozen breath. The future of a comet is shaped by the gradual loss of its volatile material and by repeated gravitational encounters within the solar system. Each close passage near the Sun removes gas and dust from the nucleus, slowly reducing its mass and altering its structure. Over many thousands of years, this steady erosion can fundamentally change the nature of the object. Some comets gradually fade as their surface ices are depleted. Activity weakens with each return as less frozen material remains available to sublight. Eventually, the nucleus may become largely inactive, no longer producing a visible coma or tail. These exhausted comets can continue to travel as dark, asteroid-like bodies that are difficult to detect. Other comets face a more sudden end. Thermal stress and internal weakness can cause fragmentation. When a nucleus splits, the pieces follow similar orbits for a time, each fragment continuing its own process of erosion. In extreme cases, close solar passage can completely destroy a comet, dispersing its remaining material into space. Gravitational encounters with planets also shape long-term outcomes. A comet may be deflected into a shorter orbit, captured into a repeating path near the inner solar system, or rejected entirely into interstellar space. Jupiter, with its strong gravity, plays a particularly important role in redirecting and removing comets from the solar system. A familiar everyday comparison is a block of ice left under the sun over many days. It does not vanish all at once. It shrinks slowly, cracks, and changes shape until little remains. The comet experiences the same gradual loss, extended across cosmic timescales. Observational surveys from the late 20th century onward have shown that many short-period comets gradually decline in brightness over successive returns, confirming the long-term fading process predicted by physical models. The distant future of today's comets is therefore defined by quiet depletion, fragmentation, or orbital escape. Their long journeys do not end in dramatic explosions, but in slow physical change driven by heat, gravity, and time. A long-period comet striking Earth represents one of the rare but high-energy events that connect deep space dynamics with planetary surface change. Unlike short-period comets that return frequently, long-period comets arrive from distant outer reservoirs and often approach Earth at very high speeds due to their extreme orbital paths. Typical impact velocities for long-period comets can exceed 50 kilometers per second, several times faster than most asteroids. At such speeds, the kinetic energy released upon impact is enormous, even for a nucleus only a few kilometers wide. The collision instantly converts motion into heat, shock waves, and high-pressure plasma. Upon atmospheric entry, intense compression of air ahead of the comet generates extreme temperatures. much of the nucleus may fragment before reaching the ground, but large pieces can survive long enough to deliver their energy to the surface. The resulting explosion would excavate a large crater, eject vast quantities of material into the atmosphere, and generate regional to global shock effects. Fine dust injected into the upper atmosphere can block sunlight for extended periods. This reduction in solar heating can disturb climate patterns, suppress photosynthesis, and disrupt food chains. The physical mechanism resembles what is observed after large volcanic eruptions, but on a potentially greater scale, depending on impact size. A familiar everyday comparison is the effect of a high-speed projectile striking water. The splash height depends not only on the object's size, but strongly on its velocity. In the same way, the destructive potential of a comet impact is controlled as much by speed as by mass. Geological evidence shows that impacts from extraterrestrial bodies have occurred repeatedly throughout Earth's history. While most known large craters are associated with asteroids, long-period comets remain a plausible contributor to rare, high-energy impact events. A single long-period comet impact would be unlikely on human timescales, yet its potential consequences illustrate how distant gravitational processes in the outer solar system can occasionally translate into sudden, dramatic change on a planetary surface. A long-period comet striking Earth represents one of the rare but high-energy events that connect deep space dynamics with planetary surface change. Unlike short-period comets that return frequently, long-period comets arrive from distant outer reservoirs and often approach Earth at very high speeds due to their extreme orbital paths. Typical impact velocities for long-period comets can exceed 50 kilometers per second, several times faster than most asteroids. At such speeds, the kinetic energy released upon impact is enormous, even for a nucleus only a few kilometers wide. The collision instantly converts motion into heat, shock waves, and high-pressure plasma. Upon atmospheric entry, intense compression of air ahead of the comet generates extreme temperatures. Much of the nucleus may fragment before reaching the ground, but large pieces can survive long enough to deliver their energy to the surface. The resulting explosion would excavate a large crater, eject vast quantities of material into the atmosphere, and generate regional to global shock effects. Fine dust injected into the upper atmosphere can block sunlight for extended periods. This reduction in solar heating can disturb climate patterns, suppress photosynthesis, and disrupt food chains. The physical mechanism resembles what is observed after large volcanic eruptions, but on a potentially greater scale depending on impact size. A familiar everyday comparison is the effect of a high-speed projectile striking water. The splash height depends not only on the object's size, but strongly on its velocity. In the same way, the disruptive potential of a comet impact is controlled as much by speed as by math. Geological evidence shows that impacts from extraterrestrial bodies have occurred repeatedly throughout Earth's history. While most known large craters are associated with asteroids, long-period comets remain a plausible contributor to rare, high-energy impact events. A single long-period comet impact would be unlikely on human timescales, yet its potential consequences illustrate how distant gravitational processes in the outer solar system can occasionally translate into sudden, dramatic change on a planetary surface. The full orbit of a long-period comet traces a span of time that far exceeds any human historical scale. Some comets require hundreds of thousands or even millions of years to complete a single journey from the outermost regions of the solar system to the vicinity of the Sun and back again. Each return marks not only a movement through space, but also a passage through deep cosmic time. When a long-period comet appears in the night sky, it is often the first time that material from the early solar system has entered the interplanetary region since before complex life existed on Earth. The object observed today may have last warmed under the Sun when early mammals were just beginning to evolve, or when no land-based life existed at all. The measurement of these immense periods relies on the same gravitational laws that govern short planetary years. By mapping the elongated shape of a comet's orbit and calculating its velocity at different distances, astronomers can determine how long it will take to complete one full cycle. These calculations reveal return intervals that stretch far beyond the span of recorded human history. A simple everyday comparison is the movement of the minute hand on a clock compared with the hour hand. The minute hand appears active and responsive. The hour hand moves so slowly that its motion is almost imperceptible over short intervals. The comet's journey unfolds on a timescale closer to the hour hand, where change becomes visible only across massive spans of time. Because of this extreme timescale, individual comets serve as physical markers of the solar system's long-term evolution. Each close approach records how repeated heating, erosion, and gravitational interaction steadily reshapes small bodies over epochs. When the path of a comet is placed alongside the history of Earth, it highlights the contrast between biological time and astronomical time. Civilizations rise and fall, while a single comet concludes only a tiny fraction of its orbital cycle. The long journey of a comet therefore offers a measurable link between motion, gravity, and time itself, demonstrating how slow, continuous physical processes shape the structure of the solar system across the deepest accessible scales of cosmic history.